Okay, next up we have Kaustubh Gadkari from CSU.
Good morning. I'm Kaustubh from Colorado State. I'm a PhD student in the computer science department. And I'm going to be talking about a bit of my work, which will go into my dissertation. My slides went away. There you go. So what problem are we trying to solve? We've known for a long time that the rate of growth of the RIB, the global default-free routing table, has been a concern for a long time. It's been growing at a rate that's faster than linear for a while now. The global RIB size also affects the FIB size because FIBs are a function of many RIBs calculated together. We think that the FIB growth is a bigger concern than RIB growth. FIB memory tends to be small, it tends to be expensive. Lookups on the FIB need to keep up with increasing line speeds. And operators, I guess you would know, have to deal with increasing line speeds as well as more lookups per second. And this makes network provisioning hard because it will keep throwing more hardware and faster hardware at the problem. This is all for IPv4. We don't know how bad IPv6 is going to make things. So our work focuses on solving this problem, and our solution is to implement FIB caching. So why cache? The short and sweet answer is performance. Cost also is involved. The way we see it, caching gives us two potential benefits. One, it reduces the memory bandwidth required for the FIB accesses. That's because we actually reduce the number of times the actual FIB on the slow memory is accessed. We also think it also gives us an opportunity to have better compression and forwarding chips. We think that on the cache we can have less compression for fast accesses, and we can store the bulk of the entries on slow memory with more compression. That gives us slower access. This may potentially be needed for the next generation of forwarding chips that have to deal with terabit per second forwarding speeds. Caching depends on this on a property of traffic called locality. So is there locality? To measure this, we took two 24-hour traces simultaneously from our friendly local neighborhood ISP, FRGP. If there's anybody from FRGP, thanks guys. We took these packet traces at two tier 1 provider links. Both links were 1 gigabit per second at the time that the traces were taken. On both links, we saw approximately 2 billion packets over the entire 24-hour period. We chunked up these traces into 5-minute intervals to see what the packet trace looked like in each 5 minutes, and that's what the graph shows. The graph essentially is what we expected. We see the well-known effect of a diurnal cycle in traffic. There is more traffic during the daytime than during the nighttime. So yes, there is locality. From our analysis, we saw that about 80,000 prefixes carry 99% of all traffic. For 90% of the traffic, you need about 1,000 prefixes. But that's a well-known result. We've known that for a long time. Jennifer Exford, Nina Taft. A lot of researchers have shown that this exists. So let's get down into the meat of our solution. Does caching work? We simulated a least recently used cache, and we saw that with our traces, we had a 96 to 99% hit rate, depending on the duration of the day. We also compared this to our optimal caching algorithm, and we found that our results are close to optimal. Even with a cold cache, when the cache is warming up, we see 87 to 91% hit rates. So yes, great, caching works. So how do we use this to build gear that uses caching? The way we see it, there are 3 barriers to doing FIB caching. One is this problem called the cache hiding problem, which we'll talk about later. Then is what do you do with the packets that actually incur a cache miss? And the third one is how does the cache behave when it is being attacked? So to solve cache hiding, our secret sauce is this thing called a cacheable FIB. What we do is we take the FIB, and we post-process it to make this thing called a cacheable FIB. And we use the cacheable FIB to serve entries in the cache. The important thing to note is that cache now preserves forwarding correctness. To explain the cache hiding problem, let's consider the following snippet of a FIB. It's a very contrived example. The FIBs are much more complex than this, we know. The point to be noted is that the 1213/16 prefix covers the 1213/14/24 prefix, and they both have a different outgoing interface. So how does cache hiding impair forwarding? Starting off with the previous example, and we have an empty cache. Suppose a packet comes along for 12.3.1.1. First thing we do is do a cache lookup to see if there is a prefix matching that packet in the cache. There isn't, so we go to the FIB. There is a longest prefix match for the 12.13.16 matches. We put that in the cache, and the packet for 12.13.1.1 goes out to the right interface 1. Then suppose a packet comes along for 12.13.14.1. As before, we do a cache lookup, and in this case, we have a hit. It matches the 12.13.16.1. And the packet goes happily along interface 1. But this is clearly wrong, because we have a more specific entry for a different interface in our FIB. So what we've seen is that the 12.13.16 entry, /16 entry in the cache has actually hidden the correct entry for the 12.13.14/24 in the FIB. This is a bad thing because you have now packets going wrong way. All sorts of bad things happen when packets go over interfaces they're not supposed to. So how do we solve the cache hiding problem? We introduce a new hole filling algorithm, which works in a way that we described. Let's start off with the previous FIB. Our algorithm goes through the FIB, selects the prefix with the shortest mask length. We check if it has any descendants. If it does, we split it into two children. We loop, we select the prefix with the shortest mask length. This guy does not have any descendants, so we delete it from the non-cacheable FIB and put it into the cacheable FIB. We go around, we select the /17 because it's the prefix with the shortest mask length. This one has a descendant, so we split it into two children. We go around, we select the /18, no descendants, so we put into the cacheable FIB. We loop, we select the other /18. This one has a descendant, so we split it into its two /19s, select the /19, put it into the cacheable FIB, and so on and so forth until we reach this stage. So we have a 12.13.14/23 and the 12.13.14/24. As before, the algorithm loops. It selects the /23. It has a descendant. In this case, the descendant is a child. So instead of adding the two /24s, we just add the missing /24. We go around. At this point, we see that both /24s actually leaves. Neither of them have any descendants. So we put them both into the cacheable FIB. The cacheable FIB has no cache hiding problem. We can cache these entries, and we don't have to deal with incorrect forwarding. But this has the potential to have, that actually introduces one more potential problem. Have we just blown up the FIB by a factor of 9, right? 4.5. We went from 2 prefixes to 9. Turns out we don't. We ran this algorithm on the table we pulled from FRGP, and we went from about 397,000 prefixes to about 432,000 prefixes, which is an increase of about 6.5%. To make sure that this wasn't, an edge artifact, or we weren't doing something funny with just FRGP, we pulled tables from route views, and we ran the same algorithm. And turns out that the percentage increase that we've seen is actually the same. This is actually not that surprising because there is research that shows that the tables themselves don't differ that much from ISP to ISP. So this percentage increase is not really a big surprise to us. But we just wanted to make sure that we were being sane. Also, since we do caching later on, and the cache size is pinned to a few tens of thousands of entries, this increase of 30,000 prefixes is pretty much irrelevant anyways. Also, since these are slowed on, we envision this FIB being slowed on slow memory, it's not a big deal. So we've just dealt with the cache hiding problem. The next barrier to caching is what do we do with the cache misses. So in our system, we queue them until they can be delivered while the cache is being updated. But what does that queue look like? How deep does it go, and how much delay do packets incur? To study this, we built our caching simulator. Packets come in, they hit the cache. If they result in a cache hit, they incur one cache lookup, and they're sent out on the outgoing interface, no problems. However, on a cache miss, we queue the packets and put them into a special cache miss buffer. When the buffer is essentially a FIFO queue, and when the packets get to the head of the queue, we do a cache fetch from the slow memory, and then the packet goes out on the write interface. We use a lookup time of 100 nanoseconds for the cache lookup and 100 microseconds for the slow memory lookup. We realize that these values are way on the higher side, probably orders of magnitude higher. We wanted to make sure that our system worked for the very worst of conditions. We expect that it will do better when we plug the actual write values in for the memory access times. So what does the cache miss buffer look like? The one thing that we see is that no data packets are ever queued. In the entire 24-hour trace, we saw about 956,000 cache misses, out of which 752,000 were TCP SYNs, the others were SYNACs. Also, the buffer utilization is fairly low. We need to have buffer space to store about 20-25 packets in any given 5-minute interval. So that's 2 out of 3 barriers to caching that we've talked about. The third and possibly the most important one is how does our cache perform under attacks? Unfortunately, attacking an LRU cache is fairly trivial. If you know the cache size, you pick those many idle prefixes. You send one packet to those many prefixes in a train, and what you get is a new cache. What we should have done, and this is an oversight on our part, is we should have simulated LFU instead when we did our caching results. This actually opens up an interesting research question. What is the appropriate cache replacement algorithm we should use? It's not a trivial question. We don't have a good answer for it right now, but we plan to take a crack at it in future work. But given that assuming that we simulate LFU, we want to know at what rate an attacker needs to send packets to replace all entries in the cache. So let's assume this cache model. The attacker knows the cache size. He picks a prefix that's idle, it's not getting packets, and he sends more packets per second to that idle prefix than the rate at which the most popular prefix in the cache gets packets. So what does this attack do? The attacker's attack prefix, which was previously idle, now becomes the top most popular prefix in the cache. The prefix that was previously the most popular becomes the second most popular, and so on and so forth, until you end up evicting the least most popular prefix from the cache. To evict all prefixes from the cache, the attacker has to use n idle prefixes, each of them at a rate that is higher than the most popular prefix. If we generalize the attack, we see that the attacker, to evict prefix I, he needs to send packets at a rate that is greater than or equal to the packet rate of the ith prefix times the rank of what the value of I. We ran these numbers on our traces. We see that if the attacker wants to replace the bottom 100 prefixes, he needs to send 5,500 packets a second. So if he wants to do, if his bar is set low and if he wants to just replace the 100 least popular prefixes, he needs to send 5,500, which is a fairly, it's very easy to do. However, if he wants to replace, say, half of the cache with 5,000 entries, he needs to send 8.7 million packets a second. If he wants to blow away the entire cache, he needs to send 17.5 million packets a second. At this point, I think this has become an attack against the network and not against the cache. The least of the operators worry should be what's in the cache, but they have network problems to deal with. We realize that our work has limitations. We don't know if our observations carry to the core. We need traces from the core to investigate. If anybody here wants to give me a trace, I'll gladly take one. However, there is research that shows that recent trends point towards traffic concentration to data centers. We believe that if this is the case, then there should be locality of traffic at the cores also. The second future work we have is what is the right cache replacement algorithm. Is there a trade-off between performance and robustness? Is LRU the right way to go? Is LFU the right way to go? We don't know. It's something we need to investigate. Also, we need a better analysis of what happens in case of cache misses. We need to investigate what is the memory bandwidth requirement in case of cache misses. And we also need to know who suffers from these cache misses. to conclude, this work is another reminder of traffic locality and also that caching works. We've seen our caching system give us 96 to 99% hit rates with a cache size of about 10,000 entries. These measurements are all carried out at the edge of the network. We've seen that we've eliminated the cache hiding problem. We've seen that in case of cache misses, we suffer fairly low queuing delays. We've also shown that our cache is fairly robust. We think attacks against the top most popular prefixes are infeasible. So let's build gear with caches. Unless we can come up with new laws of physics, we think this might be the only way to go with the next generation of forwarding chips that do terabyte per second. And this may also be required when we have larger RIBs because of IPv6 deployment. And thank you, and I'm open for questions.
So, Charles Menser with Wide Open West. I'm curious on the LRU, what sort of distribution do you see in the data you had as far as population and speed? The top one obviously was going to have a very high rate, but does it fall off dramatically or?
It does. So the topmost, from what I've seen in our traces, is about in the most popular interval, it gets about 500,000 packets in the entire 5-minute interval. But at rank for the 10,000 most popular prefixes, that's in the tens or hundreds of packets a second. So it's a fairly dramatic drop off in terms of packet rates.
Obviously, you need to do research, but it sounds like just top of the head that a attack against the top cache entries isn't feasible, but a DDoS against something in the lower part of the cache would be very feasible.
Yes, yes.
Oh, okay. So my question is, in your cache hiding problem, what kind of simulation scenario you are using? Like, what's the packet per second rate?
It actually doesn't depend on the packets per second. It just depends on what entries there are in the cache and what packets come in.
How about the wire speed? Or you don't? It's generic.
It's generic. It actually is independent of what the packet rate is. It's just what entries are there in the cache.
But you have this 10K for the cache size, right? You have 10K packets.
That is not
prefix.
The 10K prefixes is for our hit rate analysis. It does not pertain to the cache hiding. It's just an example that we use for cache hiding.
Okay. And the results was amazingly similar among all the 10, about 10 cases, right?
Yes.
Do you have any summary or conclusion for that?
Yes, actually, so there was a paper that was published, I forget where it was. It was maybe Globecom or Global Internet a couple of years ago, which shows that there is actually very little difference between the routing tables of different ISPs. So given that that is true, we did not actually expect there to be too much difference between the percentage change in the size of each ISP.
Thank you.
Sure.
David Barak, AT&T. Have you done any analysis of the impact of the cache or cacheable FIB on the multicast performance?
I'm sorry, I did not get your question.
Have you looked at multicast performance and its impact on?
No.
Okay.
This is all.
And do you even have an idea of where the lookups would how conceptually it would work?
No.
Okay.
I need to think about it.
Okay.
Thanks.
John Lewis, Atlantic Net. How does your cache hole avoidance handle learning a more specific route after a less specific route is already in the cache?
So
you cached a /16, you learn a /24 later.
So to solve that problem, we actually have a thing called the cacheable FIB. So what I described an algorithm that takes a existing FIB and processes it to actually get rid of this same problem. So there is really no learning involved in case of more specifics. So the /16 and the /24 would have been replaced by prefixes that actually cover the entire space between the /16 and /24. So there is no problem of having to relearn new routes.
Anybody else? Going once? Going twice? Thank you very much.
Thank you.